Okay, let's see how the idea of conditioning applies to continuous random variables. Okay, so remember, we have this definition of conditional probability. Let's say we have event A, that's what we're interested in, and we're given event B has occurred. And so the conditional probability is just the probability of the intersection of those events divided by the probability of B, of course, assuming B has positive probability. And we also know that for a continuous random variable, we can calculate the probability that X lands in some region, say an interval, using the PDF. So all we do is integrate over that region, integrate the PDF over that region, and that gives us the probability. And say what we want to do is calculate the probability that X lands in some region, A, and we know that it has already landed in a region B. Can we define a conditional PDF so that the conditional probability of landing in A, given that it lands in B, is the integral over A of that conditional PDF? The answer is yes. So the conditional PDF, which we write as f of x given B, of x given the event that x falls into B, that is just defined to be the PDF divided by the probability that x lands in B, so that's the rescaling, restricted to x in B and 0 otherwise. Another way to write this is to just integrate over B to get the denominator, because that's the total probability that we land in B. Okay, so this is the formula. I'm not going to show you how it's derived. We can just take for granted that this is the natural extension of conditional probability to PDFs. Let's do an example so we can see what's going on visually. Okay, so what I'm going to do here is draw for you a PDF, just a triangle in this case, and it has height 1/2 here. So the case-by-case PDF is 1/4 x from 0 to 2, and then 1 minus 1/4 x from 2 to 4, and then it's going to be 0 otherwise. Okay, and let's say that the event B is going to be from 0 to 2. Okay, so here it is. That's what I'm interested in. What is the conditional PDF of x given B? Well, the first thing I'm going to do is restrict to the set B. Okay, so only x that fall into B have positive values. So I just draw this half of the triangle now. And the next thing I need to do is rescale. So I need to calculate the probability that I fall into B, which is just the probability that I'm between 0 and 2. So I just integrate the PDF from 0 to 2, and I'm going to look in this case-by-case formula to see that there I'm 1/4 x for the PDF, and so that's going to be an 1/8 x squared from 0 to 2, and ultimately that's 1/2. And I could have seen that just by staring at this plot and convincing myself that half of the area is between 0 and 2 because the triangle is symmetric about 2. So what I do is I rescale the height of this PDF by dividing by this probability we just worked out, the probability I fall into B. And so then instead of a height of 1/2, I'm going to get a half divided by a half, and that's just 1. So the case-by-case formula for this conditional PDF is going to be the original PDF divided by the probability that I fall into B, which we just worked out. That's going to be true when I fall into B, and otherwise it's 0. Okay, so simplifying a little bit, I'm going to have the PDF whenever I'm in B divided by 1/2, because that's the probability I fall into B. And finally, I just look up the PDF in that case-by-case formula, and I see that there it's 1/4 x. So 1/4 x divided by 1/2 is x over 2. And then that's only between 0 and 2. The key intuition here, and the thing I want you to take away from this, is that f of x given B is just f of x restricted to the values of x in B. Okay, so what you do is you just take the original PDF and you cut out the places where you have B, and you rescale the height so that the total probability is 1. So the integral of this new restricted PDF is 1. That's it. So that's all a conditional PDF is. It has the same properties as a normal PDF. So all we're going to do is just restate those properties. So we're going to have non-negativity, so it can't be negative in any point. It needs to integrate to 1 over B because the total probability has to be 1. And the most interesting one is that for any event A, the conditional probability that x the random variable, falls into A, given that X has already fallen into B, I can work that conditional probability out by just integrating over the region I care about, A, and integrating the conditional PDF. Now, I could have done this directly by using the definition of conditional probability. I would have ended up with an integral over A intersect B in the numerator, and in the denominator, an integral over B. And you can just double check that that's the same thing this formula is giving you. But this is a nice, convenient thing to use sometimes. Okay, so given that X falls into B, what is the average value of X? So we know the average value of X without any conditioning is just the expectation, E of X, but we need a conditional expectation to factor in this knowledge that X falls into B. Okay, and we've already done that for discrete random variables. We're going to do it for continuous ones. So the conditional expected value of X given B, okay, so we're given the event that X falls into B. We just define that to be X given B, and that's going to be this integral over B, X weighted by the conditional PDF of X given B. And you can just see that that's going to be the integral of X with the PDF over B normalized by just the probability that you fall into B. Okay, so you could use either of these formulas. We can just state the exact same thing for the conditional expected value of a function. So the only thing that's going to change here, if we're looking at the conditional expected value of a function, is that instead of integrating X, we're integrating G of X times the conditional PDF, and you can substitute in G of X in both places in this other formula as well. Okay, and finally, it's useful to just note that we can also define conditional variance given B. Okay, and that's going to be the same thing as variance. It's going to be how you vary about the mean on average, except here I just replace every expectation with a conditional expectation. Okay, and so notice inside where I'm subtracting the expectation from X, that's a conditional expectation. And outside where I'm taking the average over these variations, that's also a conditional expectation, because I'm now fully living in this universe where X is in B. And that has to get put in both expectations. Another way to write this is just with the alternate variance formula, which I have here. Okay, let's do another example. So let's say X is uniform between -1 and 1, and I'm going to condition on this event that the absolute value of X is greater than or equal to 1/2. And I want to know the conditional PDF. Okay, so here's the original PDF. So it's just this box between -1 and 1. And I can just say that the height is going to be 1/2 because I need that the total area is 1. So the width is 2, so the height has to be 1/2, so its area is 1. And this is the region B. This is where the absolute value of X is greater than or equal to 1/2 because it's between -1 and -1/2, and then also 1/2 and 1. To get the conditional PDF, the first thing I do is I restrict to B. So I only look at this, these two parts where I fall into B. So I get these two boxes. Here's the first one, the negative side, and here is the positive side, and otherwise I'm 0. And I need to rescale so that the total area is 1. I can just check that this object, if I make the height 1, then the total area in this particular case will be 1. Okay, because I have two boxes of width 1/2 each. So I have a total width of 1, and so 1 times 1 is just 1. Okay, so writing this out as a case-by-case formula, so we can just do this a little more abstractly. So here's the definition of conditional PDF. Okay, so I'm just writing that out. So I restrict to X and B, I rescale by the probability I fall into B. The probability I fall into B from the integral is going to be from -1 to -1/2 of 1/2 dx plus 1/2 to 1/2 dx. And that's just going to be a fourth plus a fourth, which is 1/2. And we already worked that out for ourselves that this region B covers half of the area. Okay, so now plugging back in, I'm going to get just 1/2 over 1/2 whenever X falls into B, which is when the absolute value is between 1/2 and 1 and 0 otherwise. So it's 1 whenever I'm between 1/2 and 1 for the absolute value and 0 otherwise. And that looks just like this plot we derived visually. Okay, so now let's work out some other quantities for the same example, like the conditional expectation. So the formula for the conditional expectation is just the integral over b, x weighted by the conditional PDF. And so that's going to be from -1 to -1/2 x dx plus 1/2 to 1 x dx. And the reason I don't see the conditional PDF there is because it's just 1 in those two regions. And so I can just write x times 1 or just x. And you'll notice I'm also not integrating over the regions where I just have 0 because those are just going to be 0 and I don't need to worry about them. Okay, so I get half x squared from -1 to -1/2 plus half x squared half to 1, and that's going to be a fourth minus a half plus a half minus a fourth, and that's going to be 0. Okay, that makes sense. If you look at this plot, it's symmetric about 0. You expect on average the value to be 0. What about the variance? So the conditional variance of x given b, we're going to use this alternate variance formula. So we're going to get the second moment condition on b. Okay, so here I go. I'm going to write down the conditional expected value of this function x squared. And now I'm just going to do the same integration regions as before from -1 to -1/2 of x squared plus a half to 1 of x squared. And that's going to be a third x cubed between -1 and -1/2. And again, a third x cubed between half and 1. And so, okay, we can just work this out. It's -1/24 minus a third plus 1/3 minus 1/24. This works out to be -1 plus 8 minus 8 minus 1/24. The whole thing is going to be 7/12. Okay, so putting everything together, the variance of x given b is just the second moment given b minus the square of the mean given b, and that's going to be 7/12 minus 0 squared, so just 7/12. As a last thing, I'm going to use the linearity of expectation here to work out this formula. So here's another function I'm interested in. I could get it by directly computing the integral over b of 3x minus 1 squared, but another way to get this is to open up the square. Notice I have 9x squared minus 6 plus 1 given b. And so linearity of expectation lets me split this up into 3 terms. So 9 times the conditional expectation of x squared minus 6 times the conditional expectation of x plus 1. So that's linearity of expectation. And so I have these terms worked out. I have 9 times 7/12 minus 6 times 0 plus 1. And then I can just simplify. I get 63 plus 12/12. And that's 75/12. And that is 25/4. Okay, and that's it.